To begin with, it would be a good idea to have some uh, sense about how time series is different from the cross-sectional data. Now, we have done basic econometrics where we have dealt with cross-sectional data, right? Uh, and when we were actually dealing with different econometric tools and techniques, what we were doing was we were actually drawing sample from a population, right? So we were never working on the whole population, but we were actually drawing samples, and we're trying to make sure certain properties to be conditions to be fulfilled so that the exercise is approximately sort of the best possible way of estimation that we can get. Okay, so and that is why we were using Gauss Markov assumptions. So we had a series of Gauss Markov assumptions. Now in this class, some of you might not be familiar with Gauss Markov assumptions, and for them, what I have done, I have created a separate video explaining the Gauss Markov assumptions briefly for whatever is needed for this class. So you don't have to worry about it. But as I'm going with this, so just the few ideas about Gauss Markov assumptions that I'm going to tell, and you will be able to understand it. So in Gauss Markov assumption, we said that we will actually draw random samples from population, right? So what is a random sample? Random sample is basically where all different values of the variable have an equal chance of being selected, and that is why the variable is called a random sample, right? Uh, the sample is called random sample. So when I say that equal chance of being selected, so that means selection of one observation is not impacting the selection of the other observation. So which means they're actually independent. Okay, and that's something you learn in the basic statistics, right? Um, so what it means is we say that the error that we get in the model that we build from the samples we draw, we call it zero conditional mean of error. So what it means is if you take an expectation of all the errors given, like all the xi samples that you have drawn, the expectation of all the errors given xi will be zero. So let me just write it down, what I mean by that. Just give me a moment. Yeah. So what I mean by that is, so yeah, I'm not quite familiar with this Blackboard thing, so it will take me a while to actually habituate myself. It will come for sure. Expectation y given all the xi, okay, is equal to 0. Okay, so that was basically the assumption that we had for cross-sectional data. So let me just, this is something for the cross-sectional data I have done for time series here. So this is something we talked about when you're dealing with a cross-sectional data. Something like this has to be fulfilled. Okay, so we call it zero conditional mean of error. All right. Now, I will further get into a little bit of the Gauss Markov assumption, just because to make sure that it doesn't sound abstract to you. So, when you learn Gauss Markov assumption, you will come to a concept of based linear unbiased estimator. Okay, so what it means is, so we basically want to achieve an estimator which is based, which is linear, and which is unbiased. So we'll in the separate video that I talked about, I'll be covering all these different concepts. But for this purpose, uh, we'll just explain the concept of unbiased. So unbiased means whenever you are drawing a sample from the population, the mean that you take is effectively the same. Okay, and we take it as 0. Okay, because we assume for the error term we take it as 0, because we assume that when you sum the errors up, so there will be positive errors, there will be negative errors, and all of them will cancel out. So that is why we call it that is what we call it zero conditional mean. Okay, And if we have zero conditional mean, we will have, if I actually draw it, so it will look like, so let me just take a different color here. It will look like something like this. Here I plot, say, xi. Okay. And here I plot, say, ui. So I'm basically plotting the values of error with the xi value. So just make a guess what it should look like. If you remember how the scatter diagrams are plotted, so let us say, I'm plotting the scatter diagram, so different ui values for corresponding xi values. So the whole idea is they have no relationship. So xi and ui doesn't have any relationship. So what it will mean is it will have a totally undirected sort of relationship. Okay, so you really not getting any trend or anything out of this. All right, so that's the whole idea. It's all scattered without any direction or anything. All right, cool. So so that is how it should look like. If expectation of ui given xi is 0, if I make a scatter plot, it should look like this. So that is what we mean when you say a zero conditional mean of error. So they are basically independent. Now, when we come back to the, again, let's come back to the comparison of cross-sectional data and time series data. And what we will see is, um, like it might be that for time series, this property may not necessarily hold true. In time series, this property may not necessarily hold true. Okay, and there is a reason behind that. So in cross-sectional data, we will talk about population. So what is a population? So population looks something like this. So we have this big population that I started with, and then we have samples that we draw from the population. Okay, and here we have, say, all these observations. Okay, so it's like everywhere. Okay, and we actually draw some samples from this population, which looks like this. All right. Um, in time series, we may not necessarily have a population, and the reason is a time series basically we would rather I understand time series as a process. Okay, it is a process that generates data across time. You can remember it. So I repeat, time series is more like a process that generates data across time. Okay. So if I draw how it should look like, so let me define. So this is the process, and say this is along the time. Okay, and say it is generating data across this time period. So here, say these are the data generation phases, different time period where data is being generated. So let us say I just take 3 period, for example. So it's T1, it is T2, it is T3. Okay. So what is happening here, in a time series, we are actually generating data from a process. So the key point here is to remember is basically there is an underlying process that is generating the data. So if I have all the data being generated through the same process, can I necessarily consider this equation to hold true, expectation of ui given xi equal to 0? Can I consider the independence of the error terms, right? Because the process remains the same. And that is where the difference is. So the two difference basically between time series and cross-sectional data. So number one, in cross-sectional data, we talked about a population, whereas in time series, we're talking about a process. In cross-sectional data, we talked about this independence of the error terms. In time series data, we are claiming that the data is being generated through the same process. So the independence of error terms, we have to consider it carefully. Okay. And what I'm going to do in another lecture that I'm going to share with you is that I'm going to talk about the Gauss-Markov assumption in detail about cross-sectional data, and I'm going to compare that assumptions with time series. So what should be the equivalent Gauss-Markov assumption for time series data? Okay, so these are theoretical underpinning, and we need to understand it. Once we understand it, and we'll further detail about the other aspects of time series. So, all right, thank you very much. We'll end this lecture here.